All right, so this is section 9.7, and what we're going to look at in this section is how to decide whether or not a data table that's given to you represents a linear, a quadratic, or an exponential function. And really, we've done this before for linear and exponential functions in chapter 5 and chapter 7. So the big new one for today is going to be to focus on quadratic functions. Okay, but we'll review some linear and some exponential ones as well. So you have some tricks in your math toolbox. Before we get into the data tables, I just want to do a quick review of how can you tell by looking at a graph or an equation if a function is exponential, quadratic, or linear. And so from chapter 7, we looked at exponential functions, which were written in the form y equals a times b to the x. Couple reminders there. A is going to be your starting value, and b is going to be your common ratio, which is that number that you multiply by that stays the same every time for the y values. A quadratic function we talked about recently in chapter 9. This is the standard form for a quadratic, y equals ax squared plus bx plus c. You'll know if the equation's quadratic because the degree of that polynomial will always be 2. Okay, quadratic means highest power of 2. And linear is our farthest throwback. That takes us all the way back to chapter 5, when we talked about this celebrity, slope-intercept form, y equals mx plus b. Reminder, m is your slope, which we also call the rate of change. And b is our y-intercept. And we had also referred to it as our starting value many times when we were doing word problems. So looking at number 1, 2, and 3, I can see one of each. Number 1 makes a nice straight line. So if we classify that one, that would just be linear. Number 2 makes a parabola, and any parabola is going to be what we call quadratic. And this one, think back to chapter 7, I know it's been a little while, things are getting real close to the x-axis, but they're not crossing it. They start growing very slowly, and over time what happens is it starts to skyrocket and gets very big. Think of the money example that I gave you in the activity we did during class a while back. I gave you a penny on the first day, and I doubled it every single day for a month. And if you remember, what happened is by the end of 30 days, even though you only had less than $1 for those first few days, you had about $10 million at the end of the month. So even though things started growing very slowly at the beginning, over time, they grew very, very fast, and you had a very large amount of money at the end. That's what's going to happen whenever you have that exponential growth function. The other example I gave you was the paper folding. It can get you to the moon, and I believe it was 48 folds. How can you tell with the equation? Match it up with the formats that we have at the top. Number 4, what I notice is the highest power I see is 2. That makes that one quadratic. Number 5, the big giveaway in this one is the exponent that I see is x. Anytime x is my exponent, it's exponential. Number 6, very similar to number 4. Highest power I see is 2. This one's going to be quadratic. Number 7 fits the format of y equals mx plus b. There's my m, my slope, and my y-intercept would be the positive 1. This is straight up linear. Number 8, I notice there's my exponent of x, which makes it exponential. And in number 9, I don't see a power of 2, so it can't be quadratic. And I also don't see an exponent of x. And you might think, well, this doesn't really look like slope-intercept form. Is it linear? All you got to do is flip it around and rearrange it. This is the same as just writing negative x plus 3. So my slope is that little ninja negative 1, and my y-intercept is 3. So this one would be linear, with m equal to negative 1 and b equal to 3. I'm not going to put them in the chart right now. If you look at my filled-in copy of the notes, if it helps you to organize it in the chart, I took all of the numbers 1 through 9 and I placed them into the appropriate categories. So you can take a look at the handout that I linked online. So moving on to page 2, the big goal of this lesson is, well, how do we tell with a data table? If we just have a bunch of random numbers, how am I supposed to know without looking at a picture if that's going to be linear, if that's going to be exponential, or if that's going to be quadratic? And so first thing I'm going to do is give you some reminders on how do you decide that for linear and exponential, and then we'll move on to the new one that we haven't done yet, which is quadratic. So a linear model, y equals mx plus b. There's your slope-intercept form. Remember the picture we just saw before. Here's an example of something that's linear. It's a nice straight line. Whenever you're going to be looking at a data table, if it's linear, then the change in x and the change in y, meaning the gaps between the numbers, need to be based on the operations of addition or subtraction. Those are the only two operations you should be dealing with. And what you want to be looking for is a constant rate of change. And the way that we defined that back in chapter 5 was we take the change in y and we divide it by the change in x. And we called that slope, which we used the letter m to represent. So slope, rate of change mean the same thing. So here's an example of a data table. I'm trying to get rid of these red dots. See tools. Oh, sorry. There we go. Okay, back to pen. If I look at my y values right now, based on the rule above, I said it has to change by addition or subtraction. This one's not too hard to see that they're always dropping by 4. So my change in y in this case is just going to be 4, negative 4, sorry. My change in x, these are always growing by 2. So it doesn't have to be the same value as the change in y, but it still needs to be the same in this column. So my change in x has the same value. So what are the two pieces that I need? Well, if I look at slope-intercept form, I need m and I need b before I can write the equation. To get m, that's my rate of change, my slope. I'm going to take the change in y, negative 4, and divide it by the change in x, which is positive 2. And then I'm going to simplify. Negative 4 divided by 2 would be negative 2. My y-intercept, you want to be looking in the table for when your x value is equal to 0. Because when your x value is 0, you would be on the y-axis if you looked at the graph. If you're on the y-axis, that means that you have a y-intercept. So this one, they were very nice, and in the table, they actually provided me with the y-intercept. I can tell that x is equal to 0, so that means that corresponding y value needs to be b. So my y-intercept is 17. Put it together, your equation would be y equals negative 2x plus 17. There's that one. Let's look at one that's exponential. How can you tell if something is going to be exponential by looking at a data table? Well, if your end goal is to write the equation, here's our standard form we saw on the first page, a times b to the x, where a is the starting value and b is that common ratio. The graph could look like exponential growth, or it could look like exponential decay. Change in x is very similar to linear for this one. It's going to be based on addition or subtraction. So really, the x values aren't going to give away whether or not it's exponential. We're going to have to look at the y values for a little bit more information. The change in y needs to be based on multiplication or division. That's the big change here. Instead of being addition or subtraction like it was for linear, now we're using multiplication or division. And so what should you be looking for? You don't really have a rate of change anymore. It's not linear, but you want to be looking for a constant multiple, or what we often call a constant ratio, in the y values. Not the x values, but in the y values. I'm going to underline and highlight that part. That's the key. Constant multiple in the y values. So let's say I look at this data table. First thing I notice, the x's are constantly growing by 1. I'm just going to make note of that. This adds 1, this adds 1, this adds 1, this adds 1. That doesn't really give anything away yet. That could be linear at this point. Now, let's say I went into this data table without being told it was exponential. My first thing I always check, if they don't tell me what it is I check to see if it's linear. Well, from 243 to 81, if you want to see what that actually drops by, you can subtract 81 minus 243. So if I do 81 minus 243, that drops by negative 162. But then from 81 to 27, clearly it's not dropping by 162. If I do 27 minus 81, that only drops by 54. So this is clearly not going to be a linear function because the change in y is constantly changing even though the x's are always growing by 1. So addition and subtraction is not the pattern for this one. So then I try to see, okay, maybe it's multiplying or dividing by the same amount. From 243 to 81, from 81 to 27, from 27 to 9, and from 9 to 3, what it's doing is it's always dividing by 3. Or another way you could think of that, which is going to be helpful for the equation, is it's multiplying by a third. Whatever you're dividing by, you're just multiplying by the reciprocal of that number. And let's say you didn't see that. Maybe it was a little bit hard for you to notice that that was the actual ratio. I'll show you a shortcut that you can use on the calculator to see that. If I go to here's my calculator screen that should pop up. Go back to my smart notebook. Okay. First thing I notice is it dropped from 81, or I'm sorry, from 243 to 81. So what I'm going to do is just take the second value, 81, and divide it by the first value, which was 243. And what that's going to do is it's going to tell me what I multiplied by. So 0.333, if I math frac that, tells me it multiplied by a third. So then I try it for the next row. From 81 to 27, I'm going to do the same thing. I'm going to take the second value, 27, and I'm going to divide it by the previous value, which was 81. And that's going to tell me what I multiplied by to get from 81 to 27. Again, 0.333, math, enter, enter. Another 1/3. Now the numbers are getting smaller. You can probably just see this without typing it in. 27 divided by 3 is clearly 9. But well, let's say you had decimals or some crazy fractions. You can take that second value and divide it by the previous value. There's our 0.333 again, 1/3. And I won't do it again on here, but you can do it from 9 to 3. It's still going to come out to a third. So that convinces yourself that, okay, there is a constant multiple, a constant ratio here, and that constant ratio is a third. Go back to screen mode here. So right away, here, there's my b value. My common ratio is a third. You don't want to use 3 because the common ratio needs to be based off of multiplication. It can't be based off of division. So we want to use a third as opposed to 3. And the a value is the starting value. Just like I did for the y-intercept in the linear example, what I'm looking for is when x is equal to 0. It's still a y-intercept, which means it needs to have an x value of 0. So in this case, there's my a value. It's 81. So putting it together, my format I need is y equals a times b to the power of x. A is my starting value, that's 81. And my b value is a third. And I raise that to the power of x. There's my exponential model. And you could put a dot in between the 81 and the 1/3 instead of using the parentheses if you'd like. Both of those would represent multiplication. So then really the new one is, let's look at something that's quadratic. How can we tell just by looking at a bunch of numbers in a table whether or not it's going to be a quadratic function or not? Back to my pen. Same thing, the change in x is pretty boring. It's always just going to be based on addition or subtraction. It's really all about the y values that help you decide whether or not something is linear, quadratic, or exponential. Now, the change in y is also going to be based on addition or subtraction. However, why this is different from linear is because you're not going to get the change in y to be the same amount the first time that you do it. You're not going to have that constant rate of change. And once we get to the example below, I'll show you what I mean by that. You really have to go through this process twice. You need to look at two sets of differences in the y values. So you're not just looking at the first set of differences, you are focused on looking at constant second differences in the y values. That's a real big point that separates it from being linear. It takes 2 rounds in order to see something that's constant instead of just 1 round. Why 2? Well, think about what's the degree of a quadratic function? 2. So because the power is 2, it takes you 2 times in order to figure out that it's quadratic. What do I mean by that in a table? Look at this example here. First thing I'll do is just look at the x's. Clearly, they're just growing by 1. That doesn't help me at all decide right now what type of model that I have. If I look at the y values, the first thing I always like to check is, well, maybe it could be linear. This decides to drop, or it actually doesn't drop, it adds. It adds by 2, but then this adds by 4, this adds 6, and then this adds 8. Okay. Well, it's not going to be linear, because look at your change in y right here compared to your change in x. If you calculate that rate of change, 2 divided by 1 is 2, but 4 divided by 1 is 4. I don't have the same slope, the same rate of change anymore. It can't be linear. I also don't really see something that I'm constantly multiplying by to make it exponential. -1 times -5 would give me 5, but 5 times -5 wouldn't give me 13. So I don't have an exponential model. And notice I only looked at one set of differences. What I'm going to do to see if it's quadratic is I'm actually going to do this one more time using these numbers in red right over here. I'm going to take the differences in those numbers. From 2 to 4 grows by 2. From 4 to 6 grows by +2 also. And from 6 to 8 grows by +2 also. So what did I do? This was round 1 of gaps. And then I looked at a second set of differences. So I call this round 2. And what I notice is that this set of second differences is constant. So we call this having constant second differences. And anytime that happens, you have a quadratic model. So that's what I highlighted above here. Look for constant second differences in the y values. It just means you have to calculate the gaps twice instead of once. Don't worry about writing the equation for a quadratic model in a table. You're going to do that in Algebra 2. The only ones I expect you to be able to write would be linear and exponential equations from a table. All you need to be able to do if it's quadratic is identify, hey, this is a quadratic function. Pretty cool. All right, so let's practice a couple. The directions tell us which type of function best models the data in the following tables. What you want to do in order to decide that is look for common differences or common ratios. And we're going to classify these as linear, exponential, or quadratic. And as I just mentioned a moment ago, if it's linear or exponential, we're going to be able to write the equation. And if it's quadratic, we're not going to worry about that. So look at the first one. The order I always check in. I always first check, is it linear? Because to me, that's the easiest one to check first. Then I check, is it exponential? Is there some constant multiple that I'm multiplying or dividing by? And if all else fails, then I check quadratic at the end. And that's just my advice. Maybe you find one that's easier that you'd like to check first. But if you're someone who likes to follow a little format, I would go with that. I look at the first table. You can see that my x's are all growing by 1. And the x's should always be growing by addition or subtraction for any of these models. The y values, I'm going to check linear, which means I need addition or subtraction to be the same. From -1 to 2, you could either just count that or you could subtract the second row minus the first row. 2 minus -1 shows me this grows by 3. 5 minus 2 shows me this also grows by 3. And from 5 to 8, same thing. You could count it or you could subtract. 8 minus 5, hey, that grows by 3. Change in y, change in x. Looks linear to me. That slope is always 3 over 1, 3 over 1, 3 over 1. This is a linear model. where my slope is 3 over 1, which is 3, and my y-intercept in the table, do I spy a row where x is 0? I do. Because x is 0 there, my b value is equal to 5. Slope-intercept form would be y equals 3x plus 5. So first one is nice and linear. I look at the second one, and I'm going to try the same thing. I'm just going to start by looking at the x's, because I know those have to grow by addition or subtraction. Same as in the last one, this just decides to grow by 1. Now these guys, let's start with linear. From 1 to -1, it drops by 2. But then from -1 to +1, it goes up by 2. Check your rate of change. -2 divided by 1 is -2. +2 divided by +1 is +2. They have different slopes. That can't be linear. Okay, so maybe I try exponential. So I'm going to scratch this. Where's my eraser? From 1 to -1, it decides to multiply by -1. From -1 to 1, hey, it also multiplies by -1. It's looking good so far. But then, oh no, from 1 to 7, it multiplies by 7. I don't have a constant multiple, which means it can't be exponential. So I cross those two out. Last one I'm going to try, quadratic. In order to check if it's quadratic, remember, we're going to have to look to see if there's constant second differences instead of constant first differences in the y values. Why don't you erase? There we go. Get back to my pen. So I kind of already started doing this before for the first differences. Here was my change in x. And I started looking at the change in y's, but then I erased them since I didn't think it was linear. From 1 to -1, it drops by 2. From -1 to 1, it grows by +2. From 1 to 7, it grows by 6. And from 7 to 17, it grows by 10. Okay. Obviously, they're not the same number yet. So I get to do this one more time. And I'm going to do it in green. From -2 to +2, I add 4. From 2 to 6, I add 4. And from 6 to 10, I add 4. And if you look at that, there's round 2. Here's my constant second differences. Constant second. And that means it has to be quadratic. Don't worry about the equation for this one. We're not going to worry about writing quadratic equations from a table. You just need to be able to identify with the gaps whether or not it is quadratic or not. And that goes for Math Excel as well. Okay. Last table we'll take a look at. In part C, you have -2, -1, 0, and 1 for x. We have some decimals, so the calculator trick might be a little bit useful in order to see what's being multiplied or divided by. We'll see. I can tell my x values are growing by 1. My y values, I'm going to kind of skip the decimals for now. I don't like decimals if I can avoid them, so I'm going to wait just a little bit. I can see that at least from 0.5 to 1, well, that's like a half. A half to 1 grows by a half, but then from 1 to 2, it grows by 1. Clearly, it's not adding the same amount, so it's not going to be linear in this case. Let's check exponential. From 1 to 2, I would be multiplying by 2. So I'm going to check the same thing on my calculator from 0.5 to 1. Okay. On your calculator, type in 0.5, and then multiply it by 2, and you do end up at 1 times 2. From 0.25 to 0.5, you could either test it by doing 0.25 times 2, or you can do the trick I showed you in the example on the previous page. Take the second row and divide it by the first row. 0.5 divided by 0.25, if I type that in, gives me positive 2, which tells me to get from 0.25 to 0.5, I multiplied by 2. You can always check if by dividing two rows together what that constant multiple is if it's exponential. I notice there's a common pattern in the y's based on multiplication. That means it needs to be an exponential model. So here's my change in y, here's my change in x. The equation, well, it's exponential, means that we can do a times b to the x. My starting value, my a in this case, would be at 1. Oh, I didn't want to delete that. There we go. Let's do highlighter. Nope. There we go. There's my a value at 1, since it corresponds to an x value of 0. There's a. And my b value in this case, what did I multiply by every time? I multiplied by 2. So my b value is equal to 2. Now, you could write this as 1 times 2 to the x, but the Ninja 1 is optional. You don't need to write it. So I'm just going to write this equation as y equals 2 to the x. So we see this one is exponential with equation y equals 2 to the x. So there's a couple here for you to try. So why don't you pause my video right now and give these 4 a shot, and then I will write up some solutions so that I can walk you through them. Or if you see that you got them correct, you can kind of just move on and start your Math Excel. Okay. But that'll do it in terms of the new content for the notes for section 9.7. Okay. Happy mathing. All right, so if you paused me and you're ready to go through the you try problems, I'm going to write these up. What you should have noticed for the first one is that all of the x values are growing by 1. So there's my change in x. And notice that all of the y values are constantly dropping by 4. So both the change in x and the change in y have addition and subtraction patterns. That means this is a linear model. Same change in y down the entire column, same change in x down the entire column. It did not ask me to write the equation, so we do not need to write the equation for this specific question. Same directions for number 2. I always start with the change in x. I notice these grow by 1. Now this is a little harder to tell since you have some decimals to deal with. But one thing I guess we can kind of rule out right away is it's not exponential, because if I do -1 times 2.25, I'm going to get -2.25. But if I multiply by that again, if I do -2.25 times another 2.25, I'm not going to get -4. And if you're not sure of that, try that on your calculator. It's not going to come out to -4. This, therefore, cannot be exponential. So let's see if linear would work for this. To go from 0 to -0.25, is subtracting by 0.25. If you want to see how to get from -0.25 to -1, you can just take -1 and subtract -0.25. So on the calculator, if you were going to do that, where's my TI? There it is. I'm just going to take -1, and I'm going to subtract minus, in parentheses, now I'm using the small negative sign, -0.25. That tells me that from the second row to the third row, it decides to drop by -0.75. negative 0.75. From the third row, from negative 1 to negative 2.25, I'm going to take negative 2.25, and I'm going to subtract the previous row. First time I use the thick minus sign, and then in parentheses, I'm going to type in the little negative 1. Looks like that on your screen. That decides to drop by negative 1.25. And then from negative 2.25 to negative 4, we'll do the last trick here. Negative 4 minus negative 2.25. So that drops by negative 1.75. Okay, well, it's not linear because that change in y value is not the same value, whereas the change in x is staying the same the whole time. So it's not linear. We already saw before it doesn't multiply by the same amounts every time. So last up on our checklist would be to see if it's quadratic. So I'm going to take these blue numbers and I'm going to look at the gaps one more time to see if I do get a constant value after 2 rounds. So you could do the same thing we did on the calculator before. Do negative 0.75 minus negative 0.25, and you'll see it drops by negative 0.5. And that same pattern is going to hold for the rest of these. Negative 1.25 minus negative 0.75 is negative 0.5. And negative 1.75 minus negative 1.25 also confirms that this drops by negative 0.5. And look at that. There's my constant second differences in the y. So constant second differences. That's exactly what I need to check to confirm that it is a quadratic function. And we don't have to write the equation for that. Last two, find the equation of the given function. First thing we're going to have to decide is what type of function is it. Let's get the eraser tool going. Come on. There we go. So for the first one, for my change in x, I notice that this is growing by 2 every time. And for my change in y, I notice that these are always adding by 3. So I'm just doing my linear check first, and it looks like it's successful this time. Same numbers over here, same numbers over here. So I can tell right away this is linear. Before I get the equation, I need m, and I need b. My slope, change in y over change in x, would be positive 3 over positive 2, which just simplifies to 3/2. And my b value is already in the table. There's my x value of 0, corresponds to a y value of negative 4. So b in this case is negative 4. So I get y equals 3/2 x minus 4 for my equation for that one. For number 4, x's are constantly adding by 1. Doesn't help me yet, since that could be true for any of the 3 models. From 4 to 2, maybe I try to see if it's linear first. Well, it drops by 2. Oh, wait, but then it only drops by 1, even though these all stayed the same. Okay, so linear fails. Next thing I might try is it exponential? Does it multiply or divide by the same amount? And in this one, it's pretty easy to see that it's always dividing by the number 2. But what you really want to be thinking about there is what's the constant multiple, because that's going to be your b value. You're multiplying by 1/2 every time you divide by 2. You just have to take the reciprocal. So I can tell that this is exponential, since the change in y is based on division by 2 or multiplication by 1/2, which helps me decide the equation should be a times b to the x. We already got b from over here. The common ratio, that constant multiple, is 1/2. And the a value, I'll look at this row in my table. Since that's where x is 0, tells me that starting value is 2. So y equals a, starting value, 2. You could do times with a dot or with a parenthesis. I'll just do a dot for this one. 1/2. Since it's a fraction, I'm going to put it in parentheses. To the power of x. And that would be my exponential model for this one. And so that'll do it for this section. Check the Google Doc for assignments. And if you have any questions, I will be hosting an office hour that you can log into and we can do some math chatting. Have a great rest of the day.